Welcome to the Unit 1 Section 3 video on linear programming. So what linear programming is, it's a method of being able to maximize or minimize some sort of function, and that function can represent all sorts of things. It can represent production out of a factory. It can represent the amount of money that you're making in your business. And what we want to do is maximize or minimize things. So for example, we're kind of looking ahead toward applications here, but say you have a function that represents profits. Well, if you're running a business, you want to maximize those profits. So we're going to go through the method of doing something like that. And this method is called linear programming. Okay, so linear programming is a method of finding the maximum or minimum value of a function. And that function is called the objective function. And that function is going to satisfy a set of conditions called constraints. Okay, so let's talk about what these things are. A constraint is one of the inequalities of a system in a linear programming problem. So for example, and again we're looking forward toward applications a bit, but constraints are things that are going to limit that function. So for example, if you're talking about production out of a factory, you are limited to how many people you have working in that factory and how many hours a day they work in that factory. There's only so much that a human can conceivably do before there's just no possibilities of that happening. For example, say that you worked in a shop making footballs, okay? And those footballs are made by hand by a worker. Well, it would be feasible for that worker to be able to make, say, 5 footballs in a day. That would be pushing it a bit possibly, but a worker would be able to do that, okay? It would not be feasible for a worker to make 500 in a day, a single worker by hand. It's just not humanly possible that a worker can create that many footballs by themselves by hand in one day. Okay, so we're going to be limited by human constraints. We're going to be limited by time. So these are the things that we're going to be taking into account a little bit later when we start talking about applications. All right, so here's an example of a linear programming problem right here in this box. I just want to point out what these things are. So you're asked to find the maximum and or minimum values of this function. You'll notice that this is a function in terms of x and y. This is your objective function. Okay, now it says that this objective function is subject to the following constraints. Well, these right here, this list of inequalities, these would be your constraints. And we'll explore this problem here in just a moment. I just wanted to give you the setup of what a problem looks like, where the objective function is, and where the constraints are. Because we're going to be working with the constraints first, and then we will go to the objective function to find our final solution. So now that we have a little bit of the terminology and how the problem's set up under our belt, let's talk about solving a linear programming problem. Okay, so to find the solution to a set of constraints, you can do that by graphing the system of inequalities. And you can do that by finding out what the feasible region is. So I used that word earlier, feasible. You're going to end up finding what the feasible region is. And what that feasible region tells us is what types of solutions are reasonable, okay? So the points inside or on the boundary of that feasible region, these would be our feasible solutions. These are the solutions that make sense. Like I said earlier, having one person hand make 500 footballs in one day is not a feasible solution for that type of problem. Making 5 would be a more feasible solution. So here's the steps to solve a linear programming problem involving 2 variables. Okay, you're going to do this by graphing. First, you want to graph the feasible region corresponding to the system of constraints. In other words, you're just going to graph the system of inequalities. This is something that you've already done before. You've done it with 2 inequalities and you shaded the area of possible solutions. Well, now we're going to graph 3, 4, maybe 5 different inequalities, but we're still looking for the same thing. We're looking for the area that's shared, the solutions that are shared for all the inequalities. Then we're going to find the vertices of the feasible region. So once you graph the region, you're going to have corners of that shaded area, and those are the vertices of that region. We're going to test those vertices. Each one's going to come with an x and y coordinate in the objective function to find our maximum and minimum values, and that will be our answer to the problem. Now, keep in mind, an objective function may have more than one maximum or minimum. So you may have 2 different solutions that would meet the needs when we maximize or minimize the function. So let's go ahead and do a few examples of this. Okay, let's look at this first example. Let's find the maximum and minimum values of this function subject to the following constraints, and we have the constraints listed for us. Okay, so to do this, we want to get each of these inequalities in a form in which we can graph it. Well, the second and third one are in an okay form. We can graph these, but the top one, let's rearrange it just a little bit, okay, because we want to get it into slope-intercept form so we can find what our y-intercept is as our starting point so that we can graph the line using the slope. So here's the first inequality. We're going to subtract x from each side, and I'm going to lead with it so that it's in that familiar y equals mx plus b form, even though this is, of course, an inequality. And then we're going to multiply each side by -1. And when we do that, you got to remember to flip the sign because we are multiplying each side by a negative. And we get y is greater than x minus 2. All right, well, let's graph this one since this is the first one anyway. And we're going to make this one blue. We're going to make this one red. And we're going to make this one green, just so that we can keep all of our lines straight as to which one's which. Okay? Well, we know that this is going to be a dashed line, so let me go ahead and format all of this. And we're going to make it blue, and we're going to make it dashed. Okay, so we know that our y-intercept, and let's go back over here for a second, our y-intercept is going to be -2 because that's in the plus b part. So we're going to go ahead and put a little dot there on the graph at -2. And then we're going to graph our solution here. Okay? And when you graph it using the slope, which the slope is 1, then you're going to get a line that looks like this. Okay, and let me just move this line so that it's just a little bit more accurate. There we go. So there's our first line. Okay, now let's look at the other two. Well, the other two are going to be fairly easy to graph because they are either going to be a horizontal or vertical line. Let's start with x is greater than -2. Okay, well, if x is greater than -2, we find -2 on the x-axis, and we want all the values that are -2. And that turned red. Let's get this back to a red line that we're going to be drawing here. Okay, so we're going to go along here at x equals -2 along the x-axis there. Okay, so there's our second line. And notice I'm just graphing the lines right now. We'll worry about the shading here all at once, okay, because we really just want the area that's shared to be shaded. All right, so let's graph our last line. Our last line has a less than or equal to, so this time it will be a solid line, and this one we're making green. And this is y is less than or equal to 3, so we're going to find 3 on the y-axis, and we're going to graph our line like so. Okay, so now we have our lines here plotted. We are going to figure out what the shaded area is. Okay, so our shaded area is going to be the area that is shared here. And so for the first one, we have y is greater than x minus 2. So here's our x minus 2 line. This is the one that's going diagonally. And if it's greater than, we would shade everything that's above it. Okay, so above and to the left. Well, for the x is greater than negative 2 line, we would shade everything that's right of this red line. So now our shared area is this triangle in this kind of top part here, bound by this red and blue line. Then we have our green line, which is y is less than or equal to 3. And so we end up with our shaded area being essentially this triangle in the middle that is completely bound. And this is what you would expect to see. It's still a good practice to sort of do the check as you go along. But we do indeed find that this is our shaded area right here in the middle. Okay? It's good that our shaded area is bound because our next part is going to utilize what we call the corner point method. And the corner point method is finding those vertices. Okay, so we have a vertice here. We have one over here. And we have one right here. Okay, so those are our three vertices. Now that we have our three vertices, we can go in and we can now graph, or I should say, find out what those points are. Okay, so when we find out what those points are, these are the ones we're going to plug into our objective function. So this point is negative 2, 3. This point is 5, 3. And this bottom point here is negative 2, negative 4. Okay, so now once we have our points, now it's just a matter of taking our objective function, which is f of x, y equals 4x plus 3y. And we're just going to plug in our points. We're going to test all of our points. So we have f of negative 2, 3. And when we plug that in, we get 4 times negative 2 plus 3 times 3. We're just plugging in our x and y. Our second one is f of negative 2, negative 4. Again, we just plug in our x and y, negative 2 here and negative 4 here. And then we plug in our third point, f of 5, 3. And we are going to, let me see if I can make that a little neater, f of 5, 3. And we're going to just plug in our x and y for that. So our x is 5 and our y is 3. Okay? So we are going to set all three of these to see what the values are. So when we evaluate the first one, we are going to end up with 1. The second one, we end up with negative 20. And the third one, we're going to end up with 29. Okay? And so this is going to give us our final answers. So now we are just simply going to take the highest one as our maximum and the lowest value for our minimum. So we would say the max is 29 when x equals 5 and y equals 3, and the min is negative 20 when x equals negative 2 and y equals negative 4. Now, it's important to make sure that you have the x and y values stated with what your max and min are. And the reason for that is the maximum tells you what the maximum is. But what we're more concerned with is trying to find out how do we get that maximum. You know, what conditions will lead to us getting that maximum. And this will make more sense as we get into the application problems. All right, let's move on to the next example. The next example, we are asked to find the maximum and minimum values of this function subject to these constraints. Okay, so let's, like we did for the last one, let's go ahead and graph things. We'll start by graphing, and then the third one we will probably have to go ahead and make a few changes to it to get into a form that we can graph, but that's okay. These are things that we can do. Okay. So let's start by graphing the first one. So we know that we have a solid line, and we know that it's going to be greater than or equal to, but again, we'll worry about the shading here later. So we're along the x-axis, and we have x equals 0, and we want all of the x values that are 0. So we are basically going to be shading along the y-axis. Okay, so this line is going to just drop right along your x-axis. All right, so now for the second one, we have a compound inequality. We have 0 is less than or equal to y, which is less than or equal to 6. So let's read the first side by itself. We got y is greater than or equal to 0. So we know that this is going to go along the x-axis. And then we have y is less than or equal to 6, so we know we're going to go along y equals 6. 1, 2, 3, 4, 5, 6. So that would be right here. So we ended up getting 2 lines out of this compound inequality. All right, so the third one, we are going to have to do a little bit of work with, okay? So that work will involve first getting it into slope-intercept form. So to do that, we're going to start with 3x plus y is less than or equal to 15, and we are going to subtract 3x from each side, and that already gets us into our slope-intercept form. Now, the only issue here is we can't really use this y-intercept, and the reason we can't use it is because this graph does not go all the way up to 15. So let's find an alternate route. Let's look for the x-intercept. Okay? Well, to find the x-intercept, you set y equal to 0. So if we do that, we're going to end up with 3x is less than or equal to 15, because y just ends up going away. And so x is less than or equal to 5. Now, we're not so much concerned about the less than or equal to sign. We're just looking for where it intersects the x-axis. And that happens to be at 5. So we're going to go 1, 2, 3, 4, 5. We're going to plot our point there. And we're going to use that as our starting point. So we're going to come back over here. And we are going to draw a line that has a slope of -3. So you go down and over, down and over, down and over, down 3 over 1, down 3 over 1, down 3 over 1. And when you go through that entire process, you're going to end up with a line that looks like this. And we're making sure we go through that intercept. Okay? Now, let us find the area that should be shaded. That's our next step. We always like to make sure that we're getting the proper shaded area. Okay? Well, when we do x is greater than 0, greater than or equal to 0, we're going to be shading to the right. y is between these two red lines, and then we are less than on the green line. So our shaded area does happen to be right here in this box. Now, you may be wondering, why is it so important to get the right shaded area? Well, it should be fairly obvious, right? That this box is going to be our shaded area because it's the only box on the board. Well, technically, it's not the only box that you would end up with, because if this graph extended farther up, we would actually have another closed off area, which would be this triangle. So you need to see what the shaded area is by looking at each inequality, because you need to make sure you're shading the correct region. And when we do that, we end up getting a point on each of these four corners. And each of these is going to be our test point. So we have 1, 4. We have, oh, I'm sorry, looking at the wrong thing. We have 0, 6. Okay, that's a 0. We have 3, 6. We have 0, 0. And we have 5, 0. Okay, so now all we have to do at this point, take our objective function, f of x, y, equals 3x plus y. And we're going to plug in each of these points. So we're going to have f of 1, 1. Sorry, we're going to have f of 0, 0. We're going to have f of 0, 6. We're going to have f of 3, 6. And we're going to have f of 5, 0. And then all we have to do is plug in our x and y for each of these. So you have 3 of 0, or 3 times 0 plus 0. You're going to have 3 times 0 plus 6. You're going to have 3 times 3 plus 6. And you're going to have 3 times 5 plus 0. And then we're going to evaluate all four of these. So when we evaluate the first one, we get 0. When we evaluate the second one, you get 6. When you evaluate the third one, you're going to end up with 15. And when you evaluate the last one, you'll also end up with 15. So here's how we would write our answer. The max is 15 when x equals 3 and y equals 6, and when x equals 5 and y equals 0. So here you have to give both cases where you would end up with a max of 15. The min, or the minimum value, is 0 when x equals 0 and y equals 0. And that would be your answer to this one. So the process, again, take your constraints, which is your list of inequalities, graph them, find the shaded area that's shared. That is going to end up most likely being a box. Take the corners of that box, find out what those coordinates are, and then plug each of those coordinates into your objective function to see where your min and max are. And then write your answer. So there's nothing inherently hard about this. It's just a little bit of work. All right, let's move on to example 3 here and see what we can do with this one. So in this example, we've got two inequalities that need to be rewritten. So let's start with that. So first one, we've got x minus 3y is greater than or equal to negative 11. So what we want to do is greater than or equal to negative 11. We want to move the x over to the other side by subtracting. And then we want to divide everything by negative 3. So remember, when we divide by a negative, you got to flip the sign. And so we end up with 1/3 x plus 11/3. All right, well, this is all good, but it's not really helpful in terms of, like, we've got the slope, but the y-intercept's not really all that useful. So like we did before, let's use the x-intercept, see if we can get any use out of that. If we set y equal to 0 in this original one, then we get our x-intercept just being x is greater than or equal to negative 11. So we'll use negative 11 as our x-intercept and our starting point for that one. All right, before we graph anything, let's move on to the next one, because we need to rewrite this one as well. So we've got x minus 3y is less than or equal to negative 2. We are going to, like we did before, move x to the other side. And then we are going to divide by negative 3. Again, having to flip the sign because we are dividing by a negative. And we get 1/3 x plus 2/3. Now again, y-intercept not that useful, slope more useful in this form. So let's find the x-intercept so that we have a point to start with. So our x-intercept, if we plug in 0 for y, we get x is less than or equal to negative 2. And that's just for our x-intercept purposes. That just gives us a place to start. So let's go ahead and plot these two x-intercepts. We've got negative 11 for the first one, which happens to be here on the graph. And then we have negative 2, which happens to be here. Okay, so those are our two x-intercepts for those two inequalities. Now let's go ahead and graph our lines. So for the first one, the graph of the line is going to look like this. And then for the second one, our graph of the line is going to look like this. And we would expect parallel lines because the slopes are the same for both of these graphs. Okay, so there's our two lines for the first two inequalities. Now our last inequality is going to give us two lines. And let's go ahead and label it here. This is going to be in green. So we have x is 1, so we find x is 1 on the x-axis, and we do a line vertically through that line on the x-axis. So we have 1, and then we have 4, 2, 3, 4, which would be this line. Okay, now let's find the shaded region. So when we do the check for the shaded region, you're going to end up with this area right here. Okay, so now that we have our shaded region, then we can graph our corner points. So our corner points are 4 of them. 1 here, 1 here, 1 here, and 1 here. And those happen to be the points 1, 4, 4, 5, 4, 2, and 1, 1. So now that we have our 4 corner points, which are not always going to be 4, as you saw in that first example, we had 3 of them. But once we have all of our corner points, we're going to take our objective function and just simply plug in those x and y values. Okay, so we have f of 1, 1, f of 1, 4, f of 4, 2, and f of 4, 5. So we're going to just evaluate all of these. Okay, so we have 5 times 1 minus 2 times 1, 5 times 1 minus 2 times 4, 5 times 4 minus 2 times 2, and 5 times 4 minus 2 times 5. Again, we just plugged in x and y for each of these, and now when we do the math, we're going to end up with 3, negative 3, 16, and 10. So now we know what our smallest value is. It's negative 3. Our largest value is 16. So we have the maximum is 16 when x is 4 and y is 2. And the min is negative 3 when x is 1 and y is 4. Okay, so this is generally how you solve these problems. On a test, you will need to know how to do this graphing. You will need to know how to graph your system of inequalities, find the shaded area, and find your points. And then, of course, you'll need to plug in those points into the objective function to find your max and min. Well, now let's move on to applications of linear programming. Because it's nice to know how to do the process and do all the math, but applications are where you really use the math, okay? So to do a linear programming application problem, and this will be a word problem, you can go through these steps, and it's going to be essentially what we've already just done. There's just going to be a couple of things that you have to do in addition, and those couple of things are, for the most part, at the beginning here. One, you're going to have to define your variables. You need to say or state what x and y are going to be. Then you're going to have to actually write down that system of inequalities, your constraints. Those are not just going to be given to you. You're going to have to read through the problem to figure out what the constraints are. Then, from there, we're going to go into what we just did. Once you have your constraints, you're going to graph the system of inequalities. You're going to find the coordinates of the vertices. And then the other extra thing you're going to have to do is you're going to have to write an expression to be maximized or minimized, which would be your objective function. Once you have that objective function, substitute the values from the vertices into the expression, and then find your greatest or least result, whichever the problem is asking for. Okay, so that's the procedure. Let's talk about how to do these problems specifically. Okay, so here's an example, and I've kind of listed these steps in a table format so we can walk through them. So let's read the example first. You own a factory that makes soccer balls and volleyballs. The soccer balls take 3 hours to cut out and 1 hour to sew together. Volleyballs take 2 hours to cut out and 2 hours to sew together. You make a profit of $5 on the soccer balls and $4 on the volleyballs. Today, your company's employees can spend up to 18 hours on cutting and 10 hours on sewing. How many of each type of ball should be made so that your company maximizes its profit for the day? Well, first, let's define the variables. So the variables here, I'm going to let x be our soccer balls, And I'm going to let y be our volleyballs. And that's it for the first step. That's all you got to do for step number 1. Just define what your variables are. Now here's where the challenging part comes in. We've got to write our system of inequalities. Well, when we do that, we got to look at what information is given. Well, there are 2 pieces of information that are always going to be constrained because we're talking about time here. It takes so much time to cut the soccer balls. It takes so much time to cut the volleyballs. It takes so much time to sew each of them. So we have limits on how much time can be devoted to each of those because the company's employees can only spend 18 hours cutting and 10 hours sewing, and it takes so long to do one of each of those. So here's what we're going to do. Since we're talking about time, the first constraints we can start with are x is greater than or equal to 0 and y is greater than or equal to 0. Now, what these constraints mean is you have to have some time starting at 0, and you're using some time that's greater than or equal to 0. You can spend no time on it, or you can spend some time on it. But we know we can't spend negative time on it. You can't go back 4 hours ago and say, I'm going to start making the volleyballs 4 hours ago. Well, you can't do that. The time's already passed. You can only move forward in time. So our first 2 constraints are going to simply be x is greater than or equal to 0, y is greater than or equal to 0, because time simply cannot be negative. Okay? Now the other constraints, we have to kind of pick things apart a little bit. So let's read the parts that go together. We know that we can spend up to 18 hours cutting, okay? That's one process that's required to make each of the balls, okay? So we know that up to 18 hours can be spent on cutting, and it takes 3 hours to cut out a soccer ball, and it takes 2 hours to cut a volleyball. Okay, so however many soccer balls that we make, that's going to be 3 hours per soccer ball. So we can notate that as 3x. And then for volleyballs, it takes 2 hours to cut out each one. So however many volleyballs we have to spend 2 hours on each. So plus 2y. So the amount of time spending cutting out soccer balls plus the number of hours spent cutting out volleyballs, that cannot exceed 18 hours. So this has to be less than or equal to 18. Now let's go over to the sewing process. It takes 1 hour to sew together a soccer ball. It takes 2 hours to sew together a volleyball, and only 10 hours at most can be spent on sewing. Go ahead and extend that. So that leaves us with 1 hour per soccer ball, or that would be x, plus 2 hours per volleyball, so 2 times y is less than or equal to 10 hours, because we can't spend any more than 10 hours doing the sewing. So that is our last constraint. So those are 4 constraints that we have all together. So if we were to graph those constraints, and at this point we've done a lot of practice with doing the graphing by hand. Again, you're still going to need to know that for the test, but on these application problems, just doing them on your own, doing the practice problems, if you want to use a graphing utility such as Desmos, you're more than welcome to, so you can find what your shaded region is and what your points are. So that's what's happening here in step 3 and 4. You graph the system of inequalities, you find the shaded area, you find the area that's shared for all of the inequalities, and then you find the coordinates of the vertices of the polygon that's formed. And again, this is a situation where the shading is important because you had a closed off area here too. You had 2 closed off areas, and then you actually have a third one over here. So you need to know which one is going to be the area that you're looking at, your feasible region. This is why shading properly is still important. Okay, so now that we have our coordinates, we need to plug into an objective function, but we don't have an objective function yet. So let's go back up to the example and let's find the last piece of information we need. And that last piece of information is going to be our objective function. Okay, so you make a profit of $5 on soccer balls and $4 on volleyballs. Okay, that is the profit that you make, and you're trying to maximize that profit because that's what they're asking for. How do we maximize the profit? So, since this is the type of profit that we make based on each type of ball, we are going to write that as our objective equation. Okay, so I'm going to come back down here, and I'm going to write down our objective equation, which would be f of x, y, equals 5x plus 4y. That's a $5 profit per soccer ball plus a $4 profit for volleyball. And now we're just going to plug in our corner points. So we've got f of 0, 0. We've got f of 0, 5. We have f of 4, 3. And we have f of 6, 0. And when we do all of these, we're going to plug in 0 for x and 0 for y on the first one. We're going to plug in 0 for x and 5 for y on the second one. And then 4 and 3. And finally 6 and 0. So when we evaluate all these, we end up with $0. We end up with $20. We end up with the third one being $32. And the last one, $30. So now we need to select the one that's the biggest because we're maximizing profits. And so we can write as our final answer, the max profit is $32. But remember, you have to include your x and y because it's not enough to say, well, the maximum profit we can make is $32. Well, that doesn't really do you any good if you don't know how to achieve that maximum profit. So the rest of it is giving our x and y when soccer balls, or I should say when 4 soccer balls and 3 volleyballs are made. Okay, so if we want to maximize our profit, this is how we do it. We make 4 soccer balls and 3 volleyballs, and that maximizes our profit to $32. All right, let's move on to another example. In this example, we have a factory manufacturing 2 types of ice skate, racing skates and figure skates. The racing skates require 6 hours in the fabrication department, and the figure skates require 4 hours in the fabrication department. The racing skates require 1 hour in the finishing department, while the figure skates require 2 hours. The fabricating department has at most 120 hours available per day. The finishing department has no more than 40. If the profit on each racing skate is $10 and the profit on each figure skate is $12, how many of each type of skate should be manufactured to maximize profit? So very much like the last problem, we're trying to maximize what our profit's going to be. So let's start by defining the variables. We'll let x be our racing skates, and let's let y be our figure skates. Okay, so now we need to figure out what our constraints are going to be. So again, this is going to require that we pick apart the problem a little bit. Okay, so let's write the system of inequalities. And we're going to start off with taking x and y as being greater than or equal to 0. Because again, we can't spend a negative amount of time on doing any of this stuff. Okay, so that's going to be our starting point. Well, now let's kind of pick apart a little bit of the problem here and figure out what our other constraints are going to be. So we know that racing skates require 6 hours in fabrication and figure skates require 4 hours in fabrication. Okay, so this sentence is going to be a bit of a key for our first constraint, because this all deals with fabrication. Well, the fabricating department has at most 120 hours available per day. So what that means is we can spend 6 hours on a racing skate and 4 hours on a figure skate, and we can't spend any more than 120 hours. So this is how we will construct that inequality. We have 6 hours per racing skate, so that's going to be 6x, plus 4 hours per figure skate, so that's going to be 4y, and that has to be less than or equal to 120 because we can't go over 120 hours. All right, now for the next one, we're going to talk about the time in the finishing department. So the racing skates require 1 hour in finishing, figure skates require 2 hours. And the finishing department has no more than 40 hours available per day. So we're going to come back over here. We have 1 hour for a racing skate, so that's 1x, plus a figure skate requires 2 hours, so 2y, and that's got to be less than or equal to 40. Now you may be wondering, we have 120 hours available per day in the fabricating department. How is that possible when there's only 24 hours in a day? Well, what we're referring to is working hours. Okay, so if you have so many workers that work 8 hours a day, collectively we have 120 hours available based on the number of workers and the number of hours those workers are in the shop working. So this does our constraints. And while we're here, let's just quickly touch on what the objective function is going to be. So the profit on each racing skate is $10 and the profit on each figure skate is $12. How many of each type should be manufactured to maximize profit? So this line is going to be our objective function because we want to maximize the profit. Okay? So let's go down here, and here I've provided the graph based on these inequalities, and we get our corner points. Again, you can use a graphing utility, or if you would like to do it by hand, that is still an option. And then we are going to write an expression to be maximized or minimized. That is our objective function. That's what we were just talking about. So we have f of xy is equal to 10x, because we make $10 per racing skate, plus 12y, because we make $12 per figure skate. So 10x plus 12y. All right, well, you've got the corner points shown there in that graph above. And so we're just going to plug those into our objective function. So we have f of 0, 0. We have f of 0, 20. We have f of 10, 15. And we have f of 20, 10. Or 20, 0, I should say. All right, from here, we're just plugging in 10 times 0 plus 12 times 0. 10 times 0 plus 12 times 20. 10 times 10 plus 12 times 15. And then 10 times 20 plus 12 times 0. And when we evaluate all four of these, we end up with $0 for the first one, We have $240 for the second one. We get $280 for the third one. And for the last one, we end up with $200. So let me just give you a quick kind of look here at what each of these is telling us. Because we talked about the corner points, but what do they actually mean? Well, the first line is, what would we get if we made 0 figure skates and 0 racing skates? Well, you would make no money because you haven't made anything. The second line is what would happen if we made no racing skates, but we made all figure skates within those time constraints that we are given. So we can make up to 20 figure skates in a day, but we would end up with $240, which is not the maximum profit. Same thing goes if we just make racing skates. We can make 20 racing skates in a day, but we end up with a $200 profit on the racing skates. To get the highest profit, we want to make just the right balance of racing skates and figure skates, which is $280. Now, the other lines are helpful because it is nice to know how much money would we make if we made nothing but figure skates in a day. Because what if your business has a big order for figure skates? Well, you want to know what those profits are going to look like if you put all of your resources into making the figure skates. Same thing goes for the racing skates. You would make $200 if you were to make nothing but racing skates, maybe because you had a big order for them. Okay, so it's all useful information, but what we're asked for is what our maximum profit can be, and that's the answer we're going to write down. The max profit is $280, but again, we need to say how we get that $280. When 10 racing skates and 15 figure skates are made. And that would be your final answer. It makes sense that a word problem would have a bit of a word answer to it. Okay, let's do one final example to kind of wrap this whole thing up. And this time we're not talking about profits, but we're talking about a girl named Betty who works a maximum of 20 hours per week programming computers and tutoring English. And looking ahead to the end of the problem, we want to maximize how much she can earn doing those two jobs. Well, she receives $15 per hour for programming and $10 per hour for tutoring. She wishes to work between 3 and 8 hours per week on programming, so that's a constraint she put on herself. She wants to work somewhere between 3 and 8 hours on programming. She does work more hours on tutoring than she does on programming. So, to maximize the amount she earns, how many hours would she work each job? So just like before, let's start by defining our variables. Let's let X be the amount of time she spends on programming. And let's let Y be the amount of time she spends on tutoring. All right, let's figure out what our system of inequalities is going to be. And as always, when we're dealing with time, we know that X has to be greater than or equal to 0, and we know Y has to be greater than or equal to 0, because you cannot spend negative time doing either of these jobs. Well, let's see what else we have. So, if we kind of pick apart this word problem like we've done the others, well, we know that she is going to be working a maximum of 20 hours per week. So we have a maximum of 20 hours per week doing both jobs. So that's our first constraint. We know that she cannot go over 20 hours between the two jobs. So therefore, the amount of time she spends on programming plus the amount of time she spends on tutoring has got to be less than or equal to 20. Okay? So now let's move on to the next constraint. That next constraint is going to be the constraint that she places on herself. She wishes to work between 3 and 8 hours per week on programming. Okay, so since she's placed that constraint on herself, we know that programming is x. So x has to be between 3 and 8. So 3 is less than or equal to x, which is less than or equal to 8. All right, and our final constraint, we are going to look at the number of hours she works on tutoring is going to be more than what she works on in programming. So she's going to have more hours on tutoring than she does on programming. So that means that y has to be greater than x. And those would be our constraints. And when we graph those constraints, we get the graph that is shown below. And you can actually see most of the graph already in your screen here. Now, you'll notice that the x is greater than or equal to 0 and the y is greater than or equal to 0 really didn't come into play here because we had other things that kind of took care of that, such as x had to be between 3 and 8, so therefore, obviously, it's got to be greater than 0. Same thing with the y. The y gets constrained by these other two constraints, and where the y is greater than or equal to 0 really doesn't come into play. Just because it didn't come into play this time doesn't mean it won't come into play other times. So it's always a good idea when you're dealing with time, you know it's got to be positive or 0 at the very least. So, it's not bad to have that redundancy built in here a little bit. We just ended up not needing those constraints for this particular problem. But you don't know that until you do the graphing and you find out what all your constraints are. So it's just good practice to put those down when you're dealing with time. Okay. Before we move down to the bottom of the page here, let's go ahead and pick out what our objective function is going to be. Okay, so our objective function is going to be dealing with the money she's making, right? Because we're trying to maximize how much she earns. So our objective function, it would make sense that it deals with this sentence and the money. She gets $15 per hour for programming, $10 per hour for tutoring, and we want to maximize the amount that she earns. Okay, so here we have the graph. We have the feasible region, we have our corner points. Let's write down what that objective function is and finish off the problem. So our objective function would be 15x plus 10y. That's $15 per hour on programming, $10 per hour that she spends tutoring. So now that we have the objective function, we've got our coordinates. Let's go ahead and put them all in. So we have f of 3, 3. We're going to have f of 317. We're going to have f of 8, 8. And again, these are just coming off of those corner points that you have on your graph. We have f of 8, 12. Okay, so from here, all you're doing is plugging in. So we're going to have 15 times 3 plus 10 times 3. You're going to have 15 times 3 plus 10 times 17. 15 times 8 plus 10 times 8. And then you're going to have 15 times 8 plus 10 times 12. And when you evaluate all four of these, you end up with $75. You're going to end up with $215, $200, and finally $240. And so, from this list, we can clearly write down what her maximum that she earns is. So, the max she can earn is $240 when she spends 8 hours programming, and 12 hours tutoring. And that would be your final answer for this problem. So You notice that these problems take a little bit of time, but there's nothing inherently hard about them. The next section will be wrapping up Unit 1, Section 4 on absolute value functions. And that video is the next one in the series.